Okay, so this is another application of linear algebra, and these are what we're going to call network problems. Okay, so in order to get to the idea of a network, we have to get a little bit of graph theory here. A graph is something that is used to visualize the connections between two types of objects. So let's say I have these objects, and these are what we're going to call nodes. And nodes are going to be connected with what we call edges. Okay, so here I have a graph that has 4 nodes and 3 edges. If we make the edges one way, then we've moved from having a graph to having a directed graph, which is not that big of a jump, but it's pretty simple. If we change these edge names and kind of build the graph here, let's back this up a little bit. There we go. I think I can actually do this. We'll get rid of all of this. The edges and the nodes. Oops, there we go. Okay, nodes, the things that are connecting them are still edges. Okay, so I have my graph here. If I start putting numbers on these edges, like we give them kind of values of some sort, this is now what we call a weighted graph. Okay, and if I have a weighted graph that is also directed, right? And when it's directed, so this is going this way, this is going this way, and the weights that come into the node are equal to the weights going out of the node, this is what we call a network. Okay, so it's a directed graph where the weights that are going into a node must be equal to the weights going out of the node. Okay, so a typical network problem is one where you have a directed graph, but you have some unknown weights within the graph. So let's take a look at that. Okay, so we're going to build a simple network here. It's going to have 5 nodes. 1, 2, 3, 4, and 5. And it's going to have edges that connect things. So pretty simple here. Stuff's going to go into the middle. And all of that. All right, so here's the directions. This one goes to the left. That one goes down. The outside pretty much goes in a circle here. And then stuff goes through 3. Down and then back out of 3. Okay, so let's get some weights on here. We're going to say that we know that this has a weight of 20. We know that this has a weight of 10. This has a weight of 10. But we don't know the other weights. So we're going to call that x1, x2, x3, x4, and x5. Now, those are 5 unknown weights. And honestly, this does not have a unique solution, but we're going to see what range of solutions possibly work. So what you do is we're going to ultimately turn this into a Gauss-Jordan problem. We're going to do it node by node. So if I look at node 1, the 20 weight going in has to equal the x1 plus the x2 weight coming out. The x4 weight at a node 2 going in has to equal the 20 plus the x3 weight going out. At node 3, the weights of x2 plus x3 have to equal the 2 10s coming out. At node 4, the x1 and the 10 coming in has to equal the x5 going out. And at node 5, the x5 and the 10 coming in has to equal the x4 coming out. All right, so if I rewrite these equations more in the standard form, I'm going to get, let's see, x1 plus x2 is equal to 20. X3 minus x4 is going to equal negative 20. X2 plus x3 is equal to 20. X1 minus x5 is equal to negative 10. And x4 minus x5 is going to be equal to 10. All right, so the augmented matrix should look like 1, 1, 0, 0, 0, 20. 0, 0, 1, negative 1, 0, negative 20, 0, 1, 1, 0, 0, 20, 1, 0, 0, 0, negative 1, negative 10, 0, 0, 0, 1, negative 1, negative 10. Okay, so I'll leave that for you to throw into MATLAB. The resulting matrix is actually 1, 0, 0, 0, negative 1, negative 10, 0, 1, 0, 0, 1, 30, 0, 0, 1, 0, negative 1, negative 10, 0, 0, 0, 1, negative 1, 10, and then a row of zeros. Okay, so that row of zeros tells me that this is an underdetermined system. So I'm going to have multiple solutions here. So let me get rid of some of the stuff at the bottom. Don't need that right now. And let's see if we can't unpack this a bit. If I look at that as my final matrix and I parameterize x5 as t, right? Well, let's see. That means that x1 is going to be t minus 10. x2 would be 30 minus t. x3 would be t plus 10. Right? And x4, let's see, x3. Sorry, x3 should be t, that's not correct, t minus 10. So let's fix that. T minus 10. x4 is the t plus 10, right? Okay, so if I look at this, this should be a solution to that network for every value of t that's a real number. But then what would happen is some of these directional arrows would change because we would get negative flow. So we want to look at where does t have to actually lie. And the reality is that this equation with the x2 creates a restriction on me, as well as x3 and x1. x3 and x1 are basically the same equation, right? So the x3 and x1 give me a lower bound. I have to be greater than or equal to 10, right? Because if I'm not, these two go negative. The x2 has to be less than 30, because if t is bigger than 30, then the x2 is going to go negative. x4 is always going to be positive so long as t is positive, and the same with x5. So this restriction here should keep me with positive flow on every one of the edges. So usually when we're doing a network problem, we don't want to reverse the direction of the network, because that kind of takes away from the original intent of how the network was going to work. Backflow is not normally permitted. Okay, so that's a simple, way of viewing networks. We're going to take a look at another thing that are like electrical networks, which add a little bit of a more complex component to things. All right, so we're going to look at what are called Kirchhoff's law problems, okay? These involve electrical circuits, okay? So electrical circuits tend to have three different types of weights. You tend to have a weight for current, which is usually labeled as I. This is measured in amperes or amps. You have a weight for voltage, which is labeled V, which is usually measured in volts. And then you have a weight for resistance, which is usually R, which is measured in ohms, okay? Now, the basic understanding in a circuit, a simple circuit of how these things relate, is we usually say V is equal to IR. This is what's called Ohm's law, that if you take the product of the current and the resistant, you should have the voltage. Okay, so we've got a couple of things going on here, because we're going to build an electrical network, which means that we have to have flow in equal to flow out, but we also have to keep in mind this Ohm's law thing. Okay, so we have two basic rules that we have to have. One, at every junction or every node, so at each node, the big one that we're working on here is current in has to equal current out. So the big consideration here is current. Okay, number two, so that's the basic network condition. Number two is that the sum of current times resistance on a closed path has to equal the voltage on that path. Now, if you think about this, is that this is just an extension of the Ohm's law. So one says that the initial network conditions are met. Two says that we've met the rules governing Ohm's law. These two together give me what we're calling Kirchhoff's law. All right, so we're going to see if we can apply this to a pretty simple network and then see how this reduces to a Gauss-Jordan problem. All right, as much fun as it is to draw electrical networks, I'm just going to cut and paste one into this corner here. This one is really simple. It actually has two nodes, right? That's going to create two closed paths, one up top here and one in the bottom. So we have two power sources, so we're assuming like a DC direct current situation here. So these are basically batteries. This is a 7-volt battery and an 8-volt battery. I have three resistors in here. So these could be resistors or light bulbs or something like that. And then we're going to measure the current drop over each of those resistors. So we have three current measurements, I1, I2, and I3. And each resistor is rated differently. So this one is rated as 3 ohms, 2 ohms, and 4 ohms. Okay, so the first thing we have to do is we have to meet the network requirement, right? So we're going to build a system of equations here. So we have two nodes, right? Node 1 has current 1 and 3 are both going into node 1. So I1 plus I3, I3 has to give out I2, right? And in node 2, I have I2 coming in, and this has to split out to two different current paths, or current drops to I1 and I3. All right, so In my little simple graph here, this is not always the case, but in my little simple graph here, these two equations are actually identical. Oh, that got real big. Okay, so that's a little bit easier to read. There we go. So these two equations we were saying are identical. Okay, so in our system of equations, we're just going to let this be I1 minus I2 plus I3 is equal to 0. And if I've met that equation, I've met both of these. Okay, so we've met the network requirement. Everything flowing into a node has to flow back out of it. So now we've got the Ohm's law requirement, right? That the product of the current and the resistance added up on a single path has to equal its voltage. So let's take this first path here. Here I've got a resistance of 3 times a current of I1 plus a resistance of 2 times a current of I2 has to equal 7 volts. Okay, so this is the equation that represents path 1. And then there's path 2 here, and its equation says that I have to have 2 times current 2 plus 4 times current 3 has to equal 8 volts. Alright, so this is the Ohm's law set of restrictions. 3I1 plus 2I2 is 7. And 2I1, or 2I2, that is, 2I2 plus 4I3 has to equal 8. Okay, so now I've got a nice system of equations here. I've met the two parts of Kirchhoff's law, the network requirement, the Ohm's law requirement, and now we start building the augmented matrix for Gauss-Jordan. 1, negative 1, 1, 0, 3, 2, 0, 7, 0, 2, 4, 8. And if you MATLAB that, you're going to come up with this nice, neat result. Okay, so you end up with 1, 0, 0, 1, 0, 1, 0, 2, and 0, 0, 1, 1. So this means that the current at location 1 at the first resistor, the current at the first resistor should be 1 amp. The current at the second resistor should be 2 amps. And let's see, let's get it in here. The current at the third resistor should be 1 amp, not 3. 1 amp again. Okay, so what's nice about Kirchhoff's law problems is, unlike generic network problems, because this is like working with electricity, you're gonna get a definitive solution here. This is going to be a determined matrix. At the end of the day, we don't want extra electricity running around out there that we're not accounting for somewhere in the circuit. So if I built a safe circuit, I should be getting a unique solution here. So network problems can get a little bit more complex if you have more than one type of weight in the system, but this should pretty much work it out. So there's a basic network problem, there's a Kirchhoff's law problem, and then we'll play around with some of this in class. But networks are used to model a lot of things in our everyday life. So there you go.